Hello everyone, my name is Matthew Sauer. I am the manager of the global technical team focusing on Altair's AEC solutions, and today I'm going to be introducing you to SimSolid, which is a 3D analysis solution that doesn't have the usual compromises that we might have with conventional FEA. Now, if you weren't already aware, SimSolid is an innovative solution that allows you to get detailed, accurate results from a 3D CAD geometry without the need for creation of any mesh, any geometry cleanup, or any simplification of your geometry as well. And this makes it a great tool for large, complex assemblies that allow engineers to run multiple simulations in the span it would take to just create your mesh using conventional FEA, allowing you to explore more alternatives to your potential designs. It's effectively lowering the barrier of entry for complex 3D simulation and allowing engineers to answer that what-if question faster than they could have before. And SimSolid can be invaluable to solve the problems that would not be otherwise possible with 1D or 2D elements, and it can be configured to account for complex behaviors such as nonlinear material, behavior, separating contact, thermal effects, dynamic analysis, and more. The beauty of it all is that it doesn't actually require a huge investment in time to solve the problems or even to learn how the software works, thanks to its intuitive interface. And perhaps best of all, if you're already using Altair's other solutions, you might already have access to SimSolid with your Altair units. Now, the first question we get asked is, well, how does it work if it's not creating a mesh? I'm used to traditional FEA. And I think to explain that from a high level, which we can certainly go into more detail afterwards, but we want to compare it to traditional FEA naturally. So in traditional FEA, we have our geometry, and we have to divide each geometric part into smaller parts. And each of those parts we're going to call a finite element. And each element has a number of degrees of freedom, depending on the type of element that's being used, and each one has to be solved. And given the need for a large number of finite elements, the number of equations can actually get to be quite large, and this leads to a higher analysis time. SimSolid, however, works a bit differently. So instead of dividing each part into smaller elements, each part is taken as a finite element without the need for discretization. And the basis functions in the element can be of arbitrary class and are independent of the element shape as well. So this allows the DOFs to be added only where they're going to be needed, reducing the number of equations that are going to need to be solved, ultimately saving you time not having to go through that during the analysis. But also due to the absence of meshing and also geometry cleanup. Now, what do you need to use SimSolid? We've touched on this a little bit already, but it's important to maybe recap. So in order to use SimSolid, you do need some 3D solid geometry. We'll go through the different file formats that are available. With plenty of AEC solutions, it can write to these formats. You also need a SimSolid license. And if you're already working with some of our other AEC solutions like the SRAM suite or HyperMesh, for example, you likely already have access to this, and you can reach out to your account manager if you're not sure. And of course, if you need any help along the way, you're more than welcome to reach out to us. Now, what is SimSolid not doing? I don't want to paint the picture that it's going to solve all of your problems. It's great for the applications that you might have that we've already discussed, but it's not necessarily going to be great if you want to use it as a modeling tool. The geometry itself has to be adjusted outside of the software. It's also, for the most part, not doing any design code validation of any members or anything, but it does do weld evaluation according to the Euro codes. It's not doing optimization or motion analysis or explicit analysis or CFD. But we do have other solutions within the Altair suite of tools that can do that. So the best kind of analogy that I've thought of when comparing SimSolid to other solutions that you might use for your structures is to think of it as more of a digital version of physical testing and not necessarily a direct comparison to beam modeling and its associated assumptions. And throughout this presentation, I'm going to be going through some different applications that we've seen of SimSolid in AEC. And you may notice that I'm primarily focusing on structural analysis in this example, but there are absolutely other abilities to consider thermal analysis, gas bodies in between surfaces, and more. So if you'd like to explore those other features, you're more than welcome to. So we're going to jump into a demo now, and I'll be looking at the other screen, so I apologize if you're looking at the side of my head, but If you do want to follow along, we will provide this file to you to have the ability to follow along with this step-by-step demo. So I'm going to jump into SimSolid now, and you can see we have just a blank slate. We don't have anything open at the moment. But what I want to do is I want to actually start by importing my geometry. As we mentioned, you need to have that geometry come from some other source. So I can click on this import from file option. And you can see this is the file that I'm going to import. You'll notice here it's in a Parasolid file format. There are several other file formats available, and lots of these can be written from kind of your standard AEC programs. For example, we have a video that shows how to go from Revit, Autodesk Revit, into a step file that can be imported into SimSolid. This example that we're using came through Tekla, but you can see the different file formats that are available. I'm going to select this steel joint welds, click open, and you can see at the bottom of the screen it's importing the geometry. And this is what it's imported. You can see it's a fairly complex steel connection that we have that we've imported. And right now it's got all this 3D geometry represented for us. And the first step is it's coming up with this automatic connections wizard, I guess you could call it, which I'm not going to actually go through right now. I'm going to bring this up later. We can use this to basically specify any tolerances or potential imperfections in our geometry that can be mitigated through the use of this gap and penetration tolerance. But I'm not going to do that right now. I'm going to click close, and I'm going to start by actually defining a couple welds between my elements. I also want to point out that each one of these parts, I can color in different colors here. Each one of these parts has come in through my CAD model as separate parts. So that's something to consider when you're working with CAD that you want to bring into SimSolid. And we can choose how they're connected to one another, and we'll go through that now. So I'm going to click on this connections workbench, and through here, I have all these different tools to define different types of connections. And I'm going to use the seam welds option. And I can click on this and I can say create new seam welds. And I can choose a section size. I'm going to say I have a 5mm section size, and the minimum length is going to be, I'll set to 40mm. The reason I'm setting a minimum length is that there may be certain edges, like maybe the small edge of my flange, that I don't want to worry about welding, as you'll see later on. And we can choose either a primary part and weld all the secondary parts of that primary part. We can group objects together and say all those objects that I've selected should be welded together, or we can weld along a specific line or edge, amongst other options. So I'm going to go with the group weld option. And I'm going to zoom in here and I'm going to select the parts that I want to weld together. So I'm going to click on this Y flange column and the plates that are connected to that as well. So I'm just selecting them as I go through here. And you can see I've got quite a few different parts that I'm going to add to this. Make sure that each one of them is represented in my welding model. And with that, I can click the Find Welds button. And we can see all these green lines have now appeared. And if we zoom in here, they're showing the parts and the edges that have been welded. So you'll notice here that some of them have been missed, perhaps due to the size of sections that I'm using for my weld. For example, on this edge here, I don't have any weld created. And it's something I can always go back and refine. Or I could just leave it as is if that's what I wanted to do. So we can study those alternatives really quickly. I'm going to click the OK button though and just accept what I have now. And right now I've got these welds that are connecting those various parts together, but there aren't welds throughout the entire model at this time. So what I can do at this point is I can say, okay, well, with this knowledge, let me go ahead and define some automatic connections. And with the automatic connections option here, I can account for potential modeling imperfections, like maybe my CAD geometry wasn't perfect when I brought it in, and it doesn't have to be. If there are potential gaps between the parts, for example, we can account for that with this gap and penetration tolerance. And we can choose, okay, for the gap, maybe I want to have a gap tolerance of 5mm and a penetration tolerance of 5mm as well. And I want to specify a resolution level that's going to be a little bit higher. So around connections, we can make sure that we have more basically points that are connected to one another. And you might recall that we set up our welds already. So I can say, you know what, just connect only the unwelded parts. I don't want to worry about the rest of them. So I'll click the OK button. And we can see down below that SimSolid is evaluating those connections. And I can actually right click here and say, show me all the connections that you've defined. And we've got all these red and yellow shades all over our model. So what this has done for us is it's generated all these different connections based off of the parameters we set up. The red indicating the presence of bonded connections, meaning that those parts are sharing all 6 degrees of freedom, and the yellow indicating sliding connections, where it's automatically identified the bolts in our model in this case, and it's applying a sliding connection where it's going to remove that rotational constraint from those connections there. And we can modify this manually if we want to, but I'm not going to worry about doing that right now. The next step is to set up our analysis, and you can see here from the list of options that we have available, I have quite a few different analysis options. I'm just going to go with structural linear for now. I click on this, and when I open the structural linear option, I have this workbench here that allows me to then go ahead and set up my analysis model. So here I'm running the structural linear model. I'm going to define my boundary conditions. So my supports, I can choose from a variety of different support conditions for fully fixed or roller or pins or springs. I'm going to say I have an immovable support, and I can define this on a face. And I'm going to say at the bottom of my column, for the sake of continuity, that's going to be fully fixed, as well as at the top of the column here. I'm going to zoom in a little bit, and once again, fully fixed along that edge, or that face rather. I'll click OK. And if I ever wanted to see those, I can always go in and I can toggle on the display of my supports and boundary conditions and loads. By clicking on this option, we'll see all those yellow dots indicating the presence of supports at that location. Just like we could define our supports, we also have the ability to define our loads within this analysis workbench. So here we've got the pressure, loads, forces, displacements. We have bolts as well, which we could apply a tightening or pre-tensioning to if we wanted to. It's not something we're going to look at too closely right now. But I did want to look at some loads that I want to import. So I could use this remote loads tool, and I could click on the remote load option, and I can define a remote load to a face or a specific spot, for example, and specify the magnitudes and directions of those loads. Another option, however, is with that remote load tool, I can just import that remote load. So here I've got this imported remote load option. And I can import from a CSV file. So if I have this data in some other format, I can say, here's a format here, a CSV file that contains a table of the joint locations, or the load locations rather, as well as the magnitudes of those loads. And potentially it's going to have more than one load case. As you can see, I just have one load case here, but it's showing me the locations, the magnitudes, and so on. I click OK, and I clicked OK a little bit too fast to show you what was happening, but if I click on Show Boundary Conditions again, you can see here all the magnitudes and the locations where those loads are applied. And they're applied across the whole cross section. So with that in mind, we have almost everything we need to run the analysis. The only thing I haven't actually touched on yet is the materials. So here we have this default material set to steel. And if I look at the assembly, what I can do is I can actually assign my materials or apply my materials on a part-by-part basis. So here I can go into my existing steel material database, which I can build up myself as well. And I can say, you know what, do I want a mixture of materials? Do I want to modify what I have? Do I want a nonlinear material? That's totally up to me what I decide. I'm just going to go with this generic steel material, which we can see all the mechanical properties and so on. I can say, apply this to all my parts. So I click apply to all the parts. And I think I did that twice, so I'm just going to ignore this. And I'll click close. And now we can go back to our analysis and we can run our analysis. So I'm going to click the solve button. And I just want to note here that this is all done in real time. This hasn't been sped up. So we can see the solution is happening. And this is a 3D simulation. So these are all 3D CAD geometry that we have. They're solid geometry. And now we have our result. And I can actually just view how long that took. So that took 8 seconds to get the result out. And if I look a little bit closer here, I can look at displacements, for example, and I can see the displacement plot and how this model is displacing and where the maximum and minimum values might be. So I can get this nice contour plot, but I can also point to the maximum displacement of 8 millimeters at the tip of this double angle section here that I'm looking at right now. I could also do the same thing with stresses. So I can say, here's my stress plot, von Mises stress, and I want to look at where those stresses are highest. And in this case here, we have some pretty high stresses. This is a linear analysis, remember. So I may want to filter this and say, okay, show me anything that's greater than 255 MPa. So I'm going to just add that to this legend here. And I'm going to say the bottom scale, or the bottom end of this scale will be 0. And now anything that appears in red is going to be exceeding my my yield strength of my materials. So we don't want to see red. We are seeing some red here. It's good that we're seeing it, but we don't necessarily always want to see that. So we could dive a little bit deeper into this as well. And I could pick any point in my model and I could see, okay, well, what's happening at this weld location? Because I know there are some pretty high loads there. So I'm getting about 200 MPa at that one specific point that I clicked on. And I could look at any other area, like at the bottom of this plate rather. I have another weld that has even higher stress at that location. So naturally, we're going to be wanting to address that in a different way. Maybe we need a thicker plate. Maybe we need to have a larger weld. Those sorts of things can certainly be considered. And some of that we can do in SimSolid. Others we might have to do externally. One other handy feature is the ability to look at our connector forces. So here we have bolts. I can look at the bolt and nut resultant forces. So here I can get this table that's showing me which bolts have the highest and lowest forces. I can filter this, so I can say this is filtered based off of the axial force at the head, with the highest one appearing at the top of the list. And I can click the identify button here and just zoom out so we can see where this came from. And this happened to be at the kind of the edge of the connection where my highest deflecting double angle section was connecting to. And it will note that it hasn't been tightened. Now, right now we've got this model set up with bonded connections between all these different parts. However, it's totally up to us. If we wanted to consider having separating connections, we could do that and run an analysis, and it wouldn't take too much longer either. I'm not going to get into that right now, but I do want to just point out that it is available. And one other aspect that we haven't really touched on is that if we're not satisfied with the results that we're getting, how can we make changes? So I could go in and I could change the connections. I could say, you know what? I know that this weld, for example, is having some issues, this weld right here. So I could go in and I could get some more information about it. I could say, I want to edit this weld, and maybe I change the section size. So rather than 5 millimeters, it's 7 millimeters, for example. And I could apply that, click OK, and I could run my analysis again. And hopefully that would reduce my weld stresses. If we wanted to make larger changes to the model, we would probably want to do that out of SimSolid, because SimSolid is not a geometry creation tool or editing tool, but we do have one available. So right now, I'm going to just bring over Inspire. And Inspire is really cool because not only does it allow us to create the model or edit models. If I just go ahead and I say File, Import, and I import my geometry here, we're able to get the geometry represented. So we can run that solver within Inspire and get that fast solution time within this interface that also allows us to make modifications to the geometry. We can also run optimization and further types of traditional FEA from here as well. What's really cool about Inspire rather, is I can go in and I could say, you know what, I want to set up a sketch, and I want to set up a sketch on this plane here. And maybe I want to make a hole on a particular edge, or face rather, and maybe I want to even copy this hole. So I could do that really easily. So I can say here, let's set up a pattern where I copy this hole, and I want to copy it in this direction, a certain distance. So I'm going to say maybe in the opposite direction, we'll have a 250 millimeter spacing or 300 millimeter spacing, whatever works for us. This is not a real example, and I can click apply. And now I've got that geometry created. And what I can do with that is I can say, you know, now that I have those holes, let me go ahead and just extrude them from my, my parts here. And I can subtract them, and very quickly, I have a simplified castellated column here. Not something you necessarily want to do in the real world, but it is something that allows us to quickly adapt to these changes that we find from the SimSolid solver and make those modifications. And we can parameterize all these geometry inputs as well. So if I wanted to, I could have set up a parameter that defined the radius of each one of these circles, and another parameter to define the spacing between each one of these circles. Perhaps another that define the positioning. And we can look at running basically a design exploration to find the optimal position and radius and spacing of all of these that will reduce the weight, but still make sure that we're beneath our yield stress. So that's a very quick course into, or crash course rather, into SimSolid and Inspire. If you do have more questions, we hope to hear from you during the Q&A. Of course, there is lots of other material available to help dive a little bit deeper into this, and you're more than welcome to reach out again after this ATC if you have further questions. So thank you, and we hope you enjoyed this presentation.